In this video, I'm going to show you how to manipulate matrices using Mathematica. So Mathematica makes working with matrices really simple. First, let's see how I can multiply a matrix by a vector. So let's to define a matrix, let's say M, the matrix M, equal. I'm going to use the curly brackets. So I'm going to open the bracket, close the bracket. And for each row, I need another curly set of curly brackets. So let's say the first row is 1, 2, 3. The second row is 1, 1, 2, 3 as well. Or let's say 30. Let's just randomly select any numbers. 1, 13, 12, or 13, 13, 15. Then I'm going to write M and view it in matrix form. And remember, I'm writing in the same cell. When I press enter, I'm not executing anything yet. I'm just writing in the same cell. If I want to execute these lines of code, all I have to do is press shift enter. And just as a reminder, to suppress the first row, all I have to do is just put a semicolon. And then I'm going to press shift enter. And here's the matrix that I have formed with the different rows. Okay, let's multiply this by a vector. I'm going to make a vector, or define a vector x. Now look, if I define the vector with only two dimensions, and then I try to multiply m by x, remember, when I multiply a matrix by a vector, I'm using the dot, not the star. The star is only reserved for multiplying numbers by each other. So I'm going to multiply m by x, so I use the dot to indicate that I'm applying a matrix by a vector. And you get incompatible shapes because the matrix is 3 by 3 and the vector is has only 2 dimensions. So I can't apply this. I can't multiply m by x, and so I'm going to define x as a 3-dimension vector. So it has 3 numbers, 1, 2, and 34. If I multiply now m by x, I get this answer. If I call this y, I can look at y in matrix form as a row vector, and it's equal to 107, 1025, 549. Okay, so what else can I do? I can, in fact, define, let's say I would like to define the identity matrix I can basically say identity matrix, and whatever dimension I want, I can call this. Let's start from scratch. So I'm going to delete all this. If you want to start from scratch in Mathematica, you need to go to evaluation and quit kernel. Do you really want to quit kernel? Quit, and then you start from scratch. Basically, no variables are stored. So the first variable, I'm going to call it I1, which is the identity matrix 2 by 2 in a 2-dimensional vector space. And let's call another identity matrix that's 3 by 3. And notice that Mathematica is case sensitive, and that's why I put I capital and M capital. If you don't follow, if you use a different form, then Mathematica is not going to recognize your input. I'm going to view I1 in matrix form. I'm going to view I2 in matrix form, all in the same cell. Shift enter. I1 is a 2 by 2 identity matrix. I2 is a 3 by 3 identity matrix. So this is how you form an identity matrix. Now let's find the kernel of a matrix. So let's form a matrix M. Let's make it a 2 by 2 matrix. 0, 2, comma 0, 2. If you remember, the kernel of the matrix is the set of vectors which the matrix M will map into the 0 vector. So let's see how I can view this using Mathematica. And let's find another matrix S that's equal to another matrix S that's equal to 1, 2 and 0, 2, just to show you the difference between those two matrices. Now, the kernel of a matrix is found using the command null space. Null space of M gives you the sets of vectors that M will map into 0. Null space of S will give you the set of vectors that S will map into 0. Now, if you look at M, M is made out of two vectors. Let's just view them in matrix form. So M, this is M. M is made of a vector 0, 2, 0, 2. So these two vectors are linearly dependent, which means the matrix is not invertible, which means that the null space of the matrix M contains vectors that will go to, they will be mapped to the 0 vector. And indeed, the null space of M contains the vector 1, 0, which means any multiplier of the vector 1, 0, M will map it to 0. On the other hand, if you look at S, S is made out of 1, 2, and 0, 2. This matrix is made out of two vectors that are linearly independent, which means that the matrix S is invertible, and so because it's invertible, the null space of S will contain only the 0 vector, and Mathematica returns the curly brackets with nothing in between, because it could not find any non-zero vector that S will map into the 0. And let's just for clarification, M is given above as 0, 2, 0, 2. Let's define X as the vector 1, 0. What will happen when I multiply M by X? So M is 0, 2, 0, 2. X is 1, 0. When I multiply M by X, I get the 0 vector, which means X is the null space, is in the null space, or is in the kernel of M. And of course, this does not change if we multiply anything by X. 100X, this will not change. So any vector X, any vector in this form, 100X, 1X, 2X, any vector that's 1, 0, 2, 0, 3, 0, any vector with a component here that's non-zero belongs to the kernel of the matrix M, and when M is multiplied by this vector, you get the 0 vector. Okay, let's start from scratch. Evaluation, quit kernel, local, and delete everything. So one note is, if you define M 1, 2, 2, 1, for example, if you put here matrix form, then you're gonna have some problems, because M is now, you have defined M as this vector in the matrix form, and you've actually defined it in a graphics form, so you won't be able to multiply M by any vector. If I multiply M by X, you will get an error. So never put matrix form in the definition of a matrix. Basically, you view M in a matrix form, and that's how you view something in matrix form. Don't define it in matrix form. You can add some comments just to clarify things. You can print M equal. You can print M dot X equal, just in case if the so the lines of code here, this is M, I defined M and I added a semicolon, then I set print M, and then I view M in matrix form, then I defined X, print MX, and type. And that way, when I click Shift Enter, I get m equal, and this is m, mx equals this. This is just for viewing. Okay, let's now see what else we can do. Let's define a general matrix. N is equal to AB, CD, N in matrix form. Actually, I can't use N. I'm gonna use NA. Okay, so this is the matrix NA, A, B, C, D. The beauty of Mathematica is that I don't need to define or to give numbers A, B, C, D to find the inverse, for example, of the matrix. Let's call it NA inverse. The inverse of NA is a matrix. So I'm using the keyword inverse to find the inverse of NA, and I'm going to put NA inverse in matrix form. Shift Enter. This is the inverse of the matrix NA. If I want to find the determinant, so the determinant of NA, I use the keyword det, D-E-T. So the determinant of NA is equal to negative BC plus AD, basically A multiplied by D minus BC. So this is the determinant of NA. If I want to find the transpose of NA, let's call it NAT. This is transpose of NA. Shift Enter, and let's view it in matrix form. NAT in matrix form. Shift Enter, and this is the transpose of NA. This is NA, A, B, C, D, and this is the transpose AD, BC. All you have to do is just say transpose of the matrix, and you get the new matrix. Remember, Mathematica is case sensitive. Now, how do you find the eigenvalues and eigenvectors of a matrix? Let's start from scratch. Evaluation, quit kernel, local. I'm going to delete everything, remove all these cells. I don't need them. I'm going to define a new matrix M. 1, 2, 3. Let's put a symmetric matrix. So M in matrix form. Here it is. Shift Enter. This is M in matrix form. Let's say I would like to find the eigenvalues and the eigenvectors of M. All I have to do is just eigensystem of M. And let's understand the output, because you're going to use this a lot in this course, because the stress is a symmetric matrix, the strain is a symmetric matrix, and we're going to be working a lot with the eigensystems of a matrix. So when I asked for the eigensystem of M, I obtained a list. This list is made of one row that's giving me the eigenvalues, and another row that gives me the rows of the eigenvectors. So let me maybe give it a variable. I'm going to call it solution. I'm going to say solution, view the solution in matrix form. So in matrix form you can view. This is the first eigenvalue, and this is the corresponding eigenvector. The first eigenvalue and the corresponding eigenvector. This is the second eigenvalue and the corresponding eigenvector. The second eigenvalue and the corresponding eigenvector. And let's say I would like to extract eigenvalue 1. So eigenvalue 1 will be equal to solution. Now to extract, now solution is a list. Solution is a list of numbers. It has a row. The first row has the eigenvalues. The second row has the eigenvectors. So in order to extract something from a list, I use the square brackets. Not only I use two sets of the square brackets. First set and second set the first set, and then a second set inside. That differentiates it from being a Mathematica command. A Mathematica command uses one single square bracket. When I extract a value from a list, I use two square brackets. So let's say I want to extract eigenvalue 1, so I would like to get the first row, the first value. First row, first value. Oh, sorry. Right here, first row, first value, shift enter. Let's just delete the solution, so we're starting from scratch. Just to make easy for you, I define the matrix M, put a semicolon, view it in matrix form, then find its eigensystem and put it in a variable called solution, and then view that solution in matrix form. And I'm viewing solution without the in both forms, in matrix form and in a list form. And then I'm extracting eigenvalue 1 by saying that's equal to that solution, the first row, the first value. Shift enter. Indeed, I'm able to extract 3. Eigenvalue 2 is equal to the solution, the first row, the second value. Shift enter, -1. If I want to get the eigenvector, eigenvector 1 equal to the solution, the second list, the first entry. The second row, the first entry, is the first eigenvector. Shift enter, indeed I get 1, 1. And the second eigenvector is second row, the second entry. Shift enter, -1, 1. So you're going to need to know this really well for the rest of the course. How to manipulate matrices, how to find their eigenvalues and eigenvectors. Now we're going to discuss how to work with rotation matrices in Mathematica. So I'm going to start from scratch. I'm going to delete all of the above. We're going to go to evaluation, quit kernel, local, quit. So starting from scratch, nothing is saved. So the first command you'd like to know is how to create a two-dimensional rotation matrix. To create a two-dimensional rotation matrix, use the following. And notice that when I put a bracket star bracket, that means this is not a command, this is a note in Mathematica. So to create a two-dimensional rotation matrix, Q, use the command rotation matrix and just put the angle in radians. So let's say pi over 6. Shift enter, and this is your rotation matrix, and I can view it in matrix form. This is a rotation matrix of an angle pi over 6. Or you can define another one, and if you have the angle in degrees, you can put 20 degrees. Shift enter, or let's just view it in matrix form first. Q1 in matrix form, shift enter, and Q1 is cosine 20, negative sine 20, sine 20, cosine 20. And if I want to view it in a numerical form, use the command n of Q1 and view the result in matrix form as well. Shift enter, and this is the value of Q1, which is cosine 20, negative sine 20, sine 20, cosine 20. So this is how you form a rotation matrix, a two-dimensional rotation matrix. If you want a three-dimensional, to create a three-dimensional, like 3 by 3 rotation matrix, use the following. Q is equal to a rotation matrix, put the angle, so 20 degrees, and put the vector around which the rotation is occurring. So let's say this is Q3. Let's view Q3 in matrix form, and this is Q3 to rotate around a vector 1, 0, 0, rotate everything with an angle of 20 degrees. Okay, so let's now try to visualize rotation of objects. So let's work in 2D. So I'm going to create I'm going to delete this. I'm going to start from scratch, or perhaps just delete all this. Pressing Shift. I'm deleting all these. I don't want the 3 by 3 one. Let's just use the Q matrix. Shift Enter. This is Q, rotation by an angle of pi over 6. And let's first create some sort of a triangle. Now I can create a triangle with many different ways, but I'm going to say I choose to create a triangle by defining 4 points and connecting a line between those 4 points. So I'm going to define a set of points. I'm going to call them set of points. The set of points is a list, and each entry is a point. So it's a list. I used a curly bracket. Another. So I'm going to put 4 points inside. I'm going to start with a point 1, 2, or 0, 1, 5, 1, 2, 3, and the same point that I started with. So this is a set of points. I'm going to use the function polygon, which takes the set of points and makes a polygon out of it. And to view it, I'm going to use the command graphics C. Shift Enter. And here is my set of points after making a polygon. So this is C, which is the object. I'm viewing the object C. C is a polygon connecting the set of points, and the set of points is made out of points 0, 1, 5, 1, 2, 3, 0, 1. And I can, in graphics, I can ask for the view the axis. Remember, Mathematica is case sensitive, and I want the origin of the axis to be in the point 0, 0. Shift Enter, and you can, this is the triangle. Now let's rotate this triangle. Now to rotate this triangle, I'm going to take the set of points. I'm going to call new set of points. This new set of points is made out of a table where I'm going to take every row in the set of points. Set of points I gives me the row I. So each row, I'm going to multiply each row by Q, which is the rotation matrix. And this I is from 1 to 4. These are the 4 points of the set of points. Make out of them a new set of points. And new C is a new polygon made out of the new set of points. And the graphics, I'm going to open a curly bracket and close a curly bracket, make a list of C and the new C. Shift Enter, and here's the triangle, the original triangle, and the new triangle after rotation. So let's increase this angle. Instead of pi over 6, let's make it pi over 3. And here's, it's rotated more. Let's make it pi over 2, rotated by 90 degrees. and here is the triangle before and after rotation. And you can do this also in 3 dimensions. So let's do it in a 3 dimensions. So I'm going to form Q rotation matrix pi over 2. Let's make it out of around the vector 1, 1, 1. Q in matrix form. And I'm going to use the function cuboid. Cuboid C is a cuboid from point 0, 0, 0 to point 1, or let's say 3, 2, 1. Let's view that cuboid first. So graphics, 3D. Notice that compared to the previous example, I used 3D because this is a 3D object. In the previous example, I was using only 2D objects, so there was only graphics. Here, I'm using a 3D object, so I've added graphics 3D. I'm going to put C, Shift Enter, and this is the cuboid. Again, I'm going to view the axis, axes true, and axis origin 0, 0, 0. Shift Enter, and here's my cuboid, and here are the axes. Now I can apply a transformation to C using this rotation matrix, and I do this using the function geometric transformation. I'm going to take C and apply Q to it. I'm going to call the new object new C. And now view new C and C together in the same image. New C is nothing but C after you rotate it by the matrix Q. Shift Enter, and here is the cuboid after rotating around the vector 1, 1, 1 with an angle of pi over 2. Let's make this angle pi over 6, for example. And here is the object. And here is the cuboid after rotating around the axis 1, 1, 1 with an angle pi over 6. You can rotate around different axes. For example, this one, around the vector 1, 0, 0, and let's use the rotation matrix. So rotation angle of pi over 5. Shift Enter, and here's the rotation around this vector with an angle of pi over 5. Let's make it pi over 2. Shift Enter, and you can see a rotation of 90 degrees. So after that, we're going to see how a vector and a matrix change when we apply a coordinate, a change of basis. So for example, let's start from scratch. Let's delete everything. Evaluation, quit kernel. I'm going to quit kernel just so that I don't have any values stored in the memory. And I'm going to use one of the examples that we studied in the lectures. M is a matrix made out of the numbers 0.25, 0.5, 0.1, 0.5, negative 0.5, 0.5, negative 0.25, negative 0.5, 0.5. So this is M in matrix form. So this is M in matrix form, and my rotation matrix is made out of Q. Of the 3 vectors U and V. If you remember, U was equal to 0.6, 0.8, 0. I'm going to put a semicolon. V was equal to negative 0.8, 0.6, 0. And W was equal to 0, 0, 1. So those 3 vectors are orthonormal because norm U and norm V and norm W, and u dot v, u dot w, and v dot w. If I look at all this, shift enter, norm u, norm v, norm w, they're all equal to 1. U dot v, u dot w, v dot w are all equal to 0, which means u, v, and w are orthonormal. So I'm going to form my rotation matrix. It's going to be made out of 3 rows. The first row is u, the second row is v, third row is w, and I don't really need to write anything else because u is already the vector, this vector, so I already put it here and put v and put w, semicolon. If you just don't, you can view it in matrix form to ensure that your selection is correct. And indeed, this is my q. So what will happen if I, to view m in the new m is equal to q dot m dot transpose of q. So q dot m dot q transpose gives me the matrix m in the new coordinate system made out of u and v and w. And remember that I'm using the dot, not the star. I'm using the dot to multiply matrices. Shift enter. So the new m in matrix form has the following form. So the last example is a very important example because we're going to do it many times when we study the stress and the strain matrices. So again, I'm going to start from scratch, evaluate. So I'm going to delete everything. I'm going to select this whole thing and delete it, and go to evaluation, quit kernel, quit. So in this, I would like to find a coordinate system in which a matrix is diagonal. So a symmetric matrix is diagonal. So let's say S is equal to the matrix. So 3 vectors, it's a 3 by 3 matrix. So made out of 3 vectors. The first one is 1, 2, 3. The second row is 2, 1, negative 1. And the third row is 3, negative 1, 2. S in matrix form has the following form. Okay, so I would like to find the coordinate system in which the following matrix is diagonal. Basically, I would like to form the rotation matrix that's made out of the eigenvectors of S. So the first thing is I'm going to write eigen system of S. And I'm going to store this in a variable. I'm going to call this variable solution, for example. I'll call it anything. I'm going to call it solution 1. And just for visualization, I'm going to view solution 1 in matrix form. Shift enter. And as you see here, there's a lot of numerical. It's better to view n in a numerical form just to find the square root of all these numbers. So shift enter. And here is the numerical form of the solution of 1. So the first eigenvalue of the matrix S is 4.63897. Corresponding eigenvalue is this vector. Sorry, the corresponding eigenvector is this. Second eigenvalue is that number. The corresponding eigenvector is this. Third eigenvalue is this number. The corresponding eigenvector is this. Now, the same numbers are here, but these are, because Mathematica is symbolic, it hasn't really done some of the calculations, so it's better to use the function n, which basically says evaluate the numerical value of these quantities. Now, I would like to form the matrix of transformation. Now, this matrix of transformation is made out of the eigenvectors of S. So let's take eigenvector 1. The first eigenvector will be equal to the numerical value of the solution. the numerical value of the solution, the second list, or the second row, and the first column. And remember, I'm using two square brackets. I'm using two square brackets because I'm extracting a value from inside the list. Close the bracket for the numerical solution. So for the function n, shift enter, and this is your first eigenvalue. The second eigenvalue is 2. Third eigenvalue is the third. So again, the list solution, take the second row, the second entry, the second row, the third entry gives you the 3 eigenvectors. This is the first eigenvector, second eigenvector, third eigenvector. Now, if I take the dot product of EV1 with EV2, EV1 with EV3, and EV1 or 2 dot EV3, I will find the values to be 0. Negative 4 multiplied by 10 power negative 16, negative 15, negative 16, so these values are 0. Just because we have taken the numerical values, so there are some small numerical errors, but these numbers, of course, 10 power negative 16, practically are equal to 0. However, if I take eigenvalue 1 dot eigenvalue 1, I get a value of 1.996, which means these eigenvalues are not normalized. So I need to normalize them. So basically, I need to say that the eigenvalue 1 is equal to eigenvalue 1, but normalize it. Eigenvalue 2 is equal to eigenvalue 2 divided by normal eigenvalue 3 is equal to eigenvalue 3, but normalize it. Shift enter. So this is the first eigenvalue, second eigenvalue, third eigenvalue. This is the first, second, and third after making the length equal to 1, which means after dividing by their length. The rotation matrix that I need after that, Q is equal to eigenvalue 1, eigenvalue 2, eigenvalue 3. And okay, what will happen when I multiply S or Q by S by transpose of Q? You're expecting a matrix that is diagonal. So I'm going to call it S dash. S dash in matrix form. Shift enter. Indeed, S dash has diagonal entries. What are these diagonal entries? 4.64, negative 2.8, 2.158. Oh, these are the eigenvalues of S. And the other off-diagonal components are actually equal to 0. If these numbers are and these numbers can be annoying, if you want to get rid of them, you can use the command chop S dash. Chop basically takes care of values that are less than 10 power negative 15 or something like that. So when I chop it, it takes care of the very small values, and here's your resulting diagonal matrix S dash after rotating and after viewing it in the new coordinate system of its eigenvectors. And this is it for the Mathematica functions for for the linear algebra part. The rest of the course is basically the application of all what we studied here, the very small commands that we studied here, but we're going to apply them to the mechanics of solids.